today's morning on advances in solar forecasting. Esteemed experts here to talk about some of the innovations that are being made with respect to prediction science, as well as some of the derivative products and applications for forecasting. So excited to get this session going. We're going to try to kind of stay on a schedule with these talks, limiting them to about 20 minutes a piece. And ideally, if you can hold your questions to the very end, I would really appreciate it. So we can stay on schedule and break the questions well. I'm going to try to make it late. So without further ado, I'm going to turn things over to Dave Turner to give us an update on for annual data respondent network with respect to prediction. And Dave is the chief scientist for the Systems Lab, and he's also manager of atmospheric sciences for Renewable machine programs.
Thank you, Craig. So, talking to you today, I'm glad to be able to be here for another rendition of this wonderful markets and forecasting. We really talk about some of our activities as we work with our rapid prediction and resolution systems. So many of you, I hope all of you, are very aware of the high resolution rapid refresh or PERD, kind of model, deterministic model, 3 kilometers. We run 2 domains, one over the continental US, which is probably popular, but we also run it over Alaska. Very important for the Weather Service. We've been releasing this model, new versions of this model, since 2014, roughly every 2 years. The current version is version 4, which became in operation in December of 2020. It is doing forecasts out to 18 hours generally, but 4 times a day it goes out to 48 hours. We've been actively working on replacing this model, or sort of updating it with rapid refresh forecasts. We come out that this. I gave a seminar back in ESIG back in January. Go back and get a lot more details about Rufus. This way back to the presentation, but we've been developing it since 2019, basically version 4 is frozen. And its objective is to simplify those operations. We have many, over 6 or 7 different regional modeling systems, but ultimately we're going to be replaced with the Rufus system. Again, it's a 3 kilometer system, but it's both a deterministic and an ensemble system. One thing that's changed, the ensemble system now has 5 members, not the anticipated 10. But these forecasts are going to be 18 hours generally, with out 60 hours forecasts 4 times a day. At the moment, the code is currently frozen. We're doing a science evaluation right now as part of the standard handoff to NOAA. And so if it passes a science evaluation, it should become operational sometime in the spring of 2025. And you will see models like the NAMS, I resume, be retired. A couple things are important. The differences between Rufus V1 and HERD V4. Rufus has much better data assimilation, so the initialization of the model is much better, and many of those initial biases have been reduced. That was HERD V4 system after it became operational, was the DA system was leading in a slightly biased condition. We also have improved the physics of the Rufus system quite a bit. Well, one of the challenges we have is Rufus uses a different dynamic core. That's basically the part of the model that your Stokes equations, and it creates too much and too intense convection, and we've been unable to really aim that down. And so importantly for this community is that the curve will not be retired. So at the moment, the curve version 4 is going to continue to run operations parallel to Rufus V1, where until Rufus V2 comes around sometime around 2027. But those other regional models that you're using will basically be turned off when Rufus becomes operation. So, in the remaining time I have, I just thought I'd talk about some of the other activities that we're doing within NOAA's atmospheric science energy program. Talk a moment about WPIP3, offshore wind characterization experiment. Look at some evaluation of HERD V4 versus the global forecast system for winds on the East Coast. Ability of version 4 to capture wind ramp events, looking at the diagnosis variability, adding a new diagnostic to downwind solar radiation, and then perhaps using the HER as a resource characterization tool. So, skipping right into topic 1.5, the WPIP3, this is an offshore characterization experiment. It's a very tight collaboration with Department of Energy for the Technology Office, focusing on this area just south of Martha's Vineyard. The colored regions in this area indicate where there is space and wind lease is happening in that vineyard. There's already installing turbines in water right now. This is very much a coupled modeling and observing program, and started back in January of this year. We're trying to answer some really interesting questions. The East Coast of the United States, the offshore environment, is markedly different than the wind resource area you'll see in the primarily because of the big landmass just to its west. And so you can see a wide range of lower atmospheric stability associated with, for example, cold air coming from the continent over the warmer waters in the winter, first in the summer. You know, you can see a lot of influences. You know, you can see clearly a lot of pressure and sea surface temperature and a lot of grades associated with that. And so all of these things, you know, impact the ability to forecast winds, heights in this type of region. And so for this science questions here just span a whole range of things, everything going from sea breeze and upwelling, you know, to storms like nor'easters and hurricanes, precipitation. But the key part of this is what are the instruments we're deploying. So we're ready have deployed a whole wide range of both remote sensors and in-situ sensors on the surrounding islands, Block Island here on the western side, and on the eastern side, as well as Martha's Vineyard. But a key platform is we have an instrument in barge. You can see it here at the Block, next to the Woods Hole Ocean Institution. That barge is going to be deployed shortly and be out for multiple months. And we're also anticipating having a NOAA ship. The barge is on the ship this winter. But moving on to topic 2, just kind of a fast overview. The Department of Energy has been deploying these buoy mounted Doppler lidars. These are low power systems that are able to measure wind profiles up to several hundred meters at sea. And so for several years, they collected observations here, more or less in the W53 region at the so-called Hudson South and Hudson North locations. And so we wanted to use that sort of almost 2-year data set to evaluate what the version 4 is able to do currently, basically. And also, since we're at it, let's look at the global forecast system, which is, of course, a resolution model, but anyway, it's a global model system. So, some evaluation results here on the upper panel is a forecast lead time on the x-axis and the RMSE for the height wind, 80 meters, using the LiDAR errors. And so you can see that the errors, so the lighter colors are the PER, and the darker and more bold colors are the global forecast system. So you can see the PER data only go out to 2 days. And then after that, the now models are available to give us 14. And so you can clearly see the RMSE is increasing lead time. Interestingly, even at short time scales, the global forecast is actually doing a better job in the RMSE sense relative to cases. Bottom plot shows the correlation coefficient. So you can see the correlation coefficient again on the short time scales are pretty high, around 0.85 or larger, and it starts to decrease, and you can see, depending on what threshold you use, I like to use R is 0.5, and then you can start to see that beyond sort of day 6, day 7, the correlation. But we can look at this type of observations. They make measurements of the sea surface temperature and temperature at 2 meters on these buoys. And so using that sort of temperature, the differential, you get a sense of air surface stability. And you can see that some of the errors in the RMSE does depend on the lower atmospheric stability. And these are things that we want to pursue more to understand processes better. Moving to the next topic, sort of wind ramp. So when version 3 of the HERD came operation, that was the first time we actually forecast beyond 18 hours. And then the map modeling system was sort of 36-hour forecasts every 6 hours. Now, you know, the reason for this is we just don't have big enough compute within NOAA to really do that before, especially given that the size of HERD domain is the continental US, which is very large for you know, as I've already said, version 4 provides 48 forecasts for it. But after version 3 was released in 2018, we got feedback actually from Gunnar Schaefer, who's often been in this meeting historically. He's from MSDP, and he gave us this particular plot. And the reference time, the vertical reference line is the initialization times these models. And in black is basically the output from wind turbines. And you can see really on this day 1, there was a very nice ramp event. that the green model, which was the HERB, actually captured extremely well, where the other NWP models didn't recognize it at all. And so this ramp event was really huge, and this is just one example of many that he could have shared with us. But because of its ability to capture ramps, they really went almost immediately to looking at the HERB suggesting ramps to utilize that in their decision process. And so our very natural question was, we know we've improved version 4, physics in version 4, and so we're wondering, how will we do capturing wind ramps? We have summer students frequently in the laboratories, and so 2 undergraduate students did much of this analysis. And so to make it more of a exercise for summer students, we just focus. We only pick turbines that are within sort of 20 kilometers of an ASON center, basically the operation at stations and what the service runs. So we would have some idea. So we're going to look at wind ramps as seen at 10 meters because there's just not all towers across this range to make up better use of the rates. But you need a sense of the turbines here, the colors and brown sort of indicate the terrain, height as before. And we're going to use this wind ramp metric tool that was developed in NOAA, and the paper on the bottom sort of describes that tool. But that tool is going to have some sort of weighting of both the timing of the ramp as well as its intensity. The intensity being how much change of power you have in a certain time period. And so those two together come together to give you a composite score from the metric tool that we're going to have. This figure just shows basically the size of the circle shows you in that year how many wind ramps did you have. So 2020 we're using purple colors because that was her version 3. 2021 and 22 we're using these type colors because that was version 4. But the size of the circles basically indicate how many wind ramps did we see at each of those locations over the course of that year. So there's some small circles saying they're relatively few, some larger circles saying a lot, and you can sort of see this is a stare and compare type plot, but you're sort of seeing events at the different stations stayed the same for 3 years. And so then we can start to let's look at those wind ramp skills that's that wind ramp tool and say how much percent improvement or sort of degrading did version 4 have relative to version 3. So the left plot shows version 4 in 2021 versus version 3 in 2020. The right plot shows version 4 from 2022 versus version 3 in 2020. This is trying to handle that meteorology does change. But you can see there's a lot more red dots than you see the blue dots. Red is sort of an increase in skill score, with dark red being a 50% increase in skill score. Dark blue is a 50% decrease. And so you see a lot more red dots there. And so we can start to analyze these as a function of season. And so the left plot, the purples are showing basically the average skill score for version 3 for annual, as well as the 4 seasons. The cyan plots are showing the skill score, average skill score for version 4. And then the golden line using the right-hand axis, basically the skill improvement in percentage. And so you can see across all seasons, the skill is improving from somewhere from 10% in the winter time up to 30% in the summertime. And our ability to capture wind ramps with version 4 relative to version 3. And we were able to look at both up ramps as well as down ramps. The skill's a little bit different there. We have more skill with up ramps than we do with capturing down ramps. And we're working with that right now. So the next topic that we're spending time, so those were a lot of wind. We do a lot of solar with our research program. And really looking at how can we do a better job representing clouds and their variability with different systems. And the key part of this is when we think of our modeling system is the data assimilation part that initializes the model. There's the physics and the diacore that actually integrate the model forward. But then there's a lot of diagnostics that you can apply. So you can diagnose fields from the model output to get various other products. And so what this work here is trying to do is to figure out, can we use model output to improve what we diagnose? In other words, we diagnose solar variability. And so what we're showing here is a normal diurnal cycle of downward atmospheric irradiance, and a clear sky, the envelope. And then the golden line is sort of the effect of transmissivity. So the all sky solar irradiance divided by the clear sky solar irradiance. And so you can see this sort of the emissivity of the transmissivity as it's fluctuating around. And by looking at the transmissivity, you can take out the whole solar geometry aspect. To look at variability of morning hours as well as around period. So we started looking at, we have a long data set that we can look at. So we started visiting the solar fluxes as a function of cloud type, using a machine learning tool that we've developed over time to basically identify from observations low clouds, low clouds versus low stratum clouds versus mid-level clouds versus high clouds. We can break it down into different types of cloud situations. And then this is the y-axis that I'm showing is basically the standard deviation of that variability in and you can see for different cloud types, there's a lot of commonality across the different seasons. Blue is spring, the lighter blue is summer, green is fall, and yellow is winter. So for a given cloud type, there's a lot of predictability there, a lot of similarity across seasons that we can take advantage of. And what we've discovered is that this variability is generalizable across CONUS. And so by looking at different stations, there's no sensitivity to stations, is you can identify the cloud type. So if we can identify the cloud type, we can basically parameterize the solar flux variability. And so then we're working to work on this now. There's a little bit at the moment, a slightly overestimate when the variability in the sensitivity is an overestimate on the other side, but this is being worked on right now. Adjusted and lead to hopefully a new. So our last topic is sort of the climatology from, and you know, like you guys know about this well, we've been doing this a lot, resource planning, but in the end, we're going to have 7 years of per data. We're working hard to see if we can figure out how we can do reanalysis on that, make this actually more than a couple of data. But I thought I would just illustrate what we have now. Today we have 3.5 years of per analyses and forecasts available, and these are available on the cloud data summary and get to. And the model is going to continue to modify at least until 2027. And so in this aspect, I'm just going to use the 1 hour forecasts. I like the 1 hour forecasts. For those of you who know data assimilation, use data assimilation that never leaves you quite about the state. Data assimilation is not a conservative process. And so by doing 1 hour integration of the model, that allows the model to be more balanced physically. So looking at these 1 hour forecasts, you can see the mean on the upper plot and the standard deviation on the lower plot of the downwelling solar radiation around solar. You know, so you can really get the sense of how variable are the clouds, you know, what's this sort of annual cycle. And then we can, you know, we're continuing to have this discussion, you know, argument, really trying to work with DOE to figure out how to fund this. So this is a non-trivial project to ultimately make this a several decade data set. But I wanted to sort of show, you know, the left are the figures you just saw in downwelling shortwave around solar noon. The right is the mean of standard deviation of the 80 median wind speeds. And so you can see some very interesting patterns that you perhaps suspect to see in some locations. But then you can really start to see as you start breaking down the means by a function of season, moving from the winter time in the upper left to the spring lower left, summer, and then autumn in the lower right. You can really see a strong seasonal variability here. Some of these things are quite interesting. For example, how the wind speeds across the Great Lakes depend strongly on season. Even how the off the West Coast shoreline resources change dramatically as a function of season. The Southeast or the US is also interesting. So kind of with that, I'm just looking forward. We're going to continue in both NOAA as well as in our this research, renewable energy research program to really work on improving this day ahead rapid basis. We're already doing these double click trees to look at comparing models to observations, evaluating physics, evaluating data simulation methods, developing new diagnostics. We're already working with version 2. That's already happening today. And we're doing a variety of analyses to really look at the predictive performance. And hopefully we're take some of this stuff and translate it into our forecast system. But unfortunately, and I mentioned this a lot seminar back in January, Rufus is an ensemble system. One of the things that we need to do more is to start to look at the spread and skill among members, especially for renewable purposes. Rufus was really designed to be a convective. So it's really looking at getting the spread and the skill right in convection. You realize it's not the best better, but how well is it doing for application in this? So that's something we still need to look at it a little bit more. My code is frozen, working V2 and said that. ultimately, there's been this pioneering work over the last several years in particular of using data-driven AI-driven weather prediction models. And so we're working also as a way to come up with effectively if we build a seal system. And then the need for this. So if you have any questions, please happy to take them there.
Thanks, Dave. Next, we're going to move over to the forecast provider side and hear from Armin Kahnert from Energy and Meteo Systems. He's a senior meteorologist in Energy and Meteo Systems in Germany. He's going to talk about an alternative to the standard probabilistic forecast.
Yeah, so good. Then let's get started. So good morning, thanks, Craig. So I'm going to talk about spreads and gradient spreads. So it's more the general topic is more or less situation awareness in our forecast and also probabilistic forecasting. So basically I'm from German forecast vendor from Energy Meteor, and we are our Energy Meteor is one of three companies dealing with renewable energies. And besides Energy Meteor systems, which offer forecast for so for renewable energy forecasting, we also do virtual power plants and also grid management. And here especially, for example, just forecast of vertical grid. And our goal is 100% renewable energies. So that's my agenda. And first of all, I will talk about situation awareness and forecasting and why it's important, or especially important. And then I will go more into detail concerning the spread and gradient spreads as an alternative to the standard approach, which is one-time forecasting when it comes to probabilistic forecasting. So yeah, I will give you then some examples and short some. So why situational awareness? So basically, every forecast is an error. And sometimes the error is small and sometimes it's large. But it's the large error which matter. So they are expensive and these tail end events, like for example, icing or high wind cutouts or smoke or heat, that are really the events which matter. And we cannot avoid the errors, but we can be to certain circumstances, prepared. And that's why it needs situational awareness. So the goal is to provide proactive information on the expected forecast error. So it's some kind of uncertainty information. But when it comes to that, we have to ask some central questions like, how is the uncertainty information used in decision making? What is the exact process? And who, and that's very important, who is by the operator, or by the market participant, or by an algorithm, and how is this information evaluated. And there are different ways to achieve this situation awareness. And since most of the renewable forecast errors are weather driven, what we can do is we can issue some kind of weather warning or weather report, for example, operators, so that they are aware that there might be, for example, an event. And that's what I will focus today on. There are also the approaches to probabilistic forecast or the scenario forecast. So you use different types of forecast scenarios. And regarding the forecast scenarios, we use the spread and the gradient spread, which is some kind of NWP approach. So basically, the renewable energy forecast derived from different NWP models, like for example, some of the answer model. And so this consists of these models, and the spread is not simply in and the max of the bandwidth of these different weather models. So it defines the weather-related uncertainty of the power forecast. And as you probably know, random situations are especially important. So it's also good to have something like a gradient or ramp forecast. What we can do is we can calculate the ramp or the gradient of the weather model in a time series, and then we can define the weather-related uncertainty of the ramps in time and steepness, the how steep are the ramps and how steep are the micro ramps. That's the gradient spread. So the spread and the gradient spreads can be used to determine some kind of worst case risk or unexpected losses or overproduction. Spread and gradient spread, and that's also important to mention, can also be derived from ensemble prediction systems, like for example, enter EPS or the TMW EPS. So basically, we have here an example now, and this is a simple forecast, so wind power forecast for a portfolio. And this is derived from different NWP and the model, and the main forecast lies somewhere in between these NWP models. And now we define the spread as the min and max of the models. And one has to mention that the models which are used to determine this spread has to be reliable with models which are most anti-correlated. So the spread min and the spread max are the min and max of the different weather forecasts in the weather models. And that's an example for gradient spread. So here in gradient, you can see the different ramping situations or gradient from the different NWP models. And the spread now shows the uncertainty of these ramping. Positive gradient means there is an upward ramp, and the negative gradient means there is a downward. And if I stack these two plots up on each other, then we can see that, for example, for the upward ramp on the left, this ramp is quite certain. So you can see that there is only a small gradient spread on the lower ramp, but the downward ramp on the right-hand side is much more uncertain. So there is definitely a model which predicts much steeper ramp here, so there is a greater uncertainty in the ramping. So when it comes to probabilistic forecast, the state of the art, or one state of the art approach is to use quantile forecast, often referred to as confidence band, confidence intervals, or percentile forecasts. And so basically the quantile forecast is based on an average historical forecast error, like for example, for fluid level or on a single part. So you need a lot of data, historical data, and then you derive some kind of average band which lies around the main forecast. And the advantage of this approach is that you can define so that you have well-defined probabilities like P80, P20 or P10 and P9. But the clear disadvantage here is that this approach mostly has a weak dependence on the current weather situation. So to get this confidence intervals, you use historical data and assume that the forecast error will be also that kind or will be also valid in the future. But this often fails during extreme situations, like for example icing or wind clouds or crossing low pressure systems. So, and the spread here has the big advantage. So as it's based on the NWP models, that it's has a clear relation to the recent weather pattern. But of course, the disadvantage is that there are not so well defined probabilities. But you get an answer, so a maximum and minimum, and that's kind of worst case scenario. And this latter point can be addressed by using EPS data. So now some examples here. So these are in fact case studies, and the examples are only from wind power, but you can also apply this approach to solar power. So the first example is a crossing low pressure system across the Great Plains. You often have this weather pattern for example, during springtime across Texas, Oklahoma. You have that low pressure systems with strong thunderstorms and large uncertainty. And what we often observe here is that the wind power production drops right behind the thunderstorms. And what you can see here in the plot is that the main forecast is again in red, and the P20 and P80 quantile forecast, which is derived from historical measurements, is in green. And the NWP spread is in light red here. So, and you can see that the NWP spread is in these extreme situations a much better indicator for the uncertainty. So there are definitely models, like for example the Bremer, which can simulate this situation, but not always. And these models indicate here, for example, that there might be a drop in the wind power production. So when you know that this situation occurs, you can use the NWP spread to have a better risk assessment to certain. So yeah, that's the first example. And the second example, and that's quite interesting, is a major icing event. So this is on a single farm level here. And you cannot use only the NWP models to determine the spread, but you can also use other kind of, let's say, extreme weather forecasts or worst case forecasts. Like for example, here the spread minimum is some kind of forecast which has incorporated icing, so the effect of icing. And here you can see that this is a much better indicator again, like for example, 2020 quantile forecast here, which is much too tight and does not explain the uncertainty in this situation. The last example here is also a typical example for the Great Plains in the US. So you have the typical diurnal cycle in wind power production with a maximum during nighttime. So you can see that on succeeding days here that there is a wind production maximum at night. This is due to the low level jet, and then you get a drop in wind power production in the morning hours, and that drop might be steeper than predicted, or it's often steeper than predicted. And as you can see in the lower plots here is again the ramp forecast, the gradient forecast. There are some models which can model this steep decrease, for example. And so you can see that there is a risk of steep downward ramps in this gradient approach here. And this also applies for other ramp situations that not only for the cycle, but this is a very prominent example here. Yeah, so to come to an end now, spread and gradient spread a scenario-based approach to address our forecast uncertainty in the sense of worst case scenario. So I have to mention that that can be used to determine the worst case risk or the weather-related worst case risk, and they are derived from the numerical weather output, and they show the uncertainty in the production level. And this gradient spread approach indicates the uncertainty of specific ramp events in time and steepness. So if the ramp is steeper than predicted, or might be steeper than predicted. So, and as opposed to quantile forecast, which is the state-of-the-art approach, this approach is very sensitive to the current weather pattern, and it performs quite well during extreme events like icing, ramps, and wind clouds. But also during, for example, solar events like dust events, fog or snow. So it's something for the extreme events. Yeah, that's all I got. Thank you.
Thanks for being good stuff. Now we're going to move on into another talk this week by Pascal Storck, who's head of technology. He's going to talk about cloud nowcasting for short-term solar energy predictions, building upon what we heard from Eric yesterday. Pascal.
Thank you. You hear me? All right. Thank you, Craig. Thank you, Charlie, for inviting me back. For 17 years, I mean, I know, but all the way since 2008. I remember sitting at these conferences, that load thing, that scare everybody.
Yes.
Like, how are we gonna do that? I remember sitting freezing out cold in the office with Charlie. And people were saying, how are we gonna do 1,000 gigawatts? How are we gonna forecast this? How are we gonna integrate that? Now we're on our way in some of these markets to hundreds of gigawatts. Somehow we did it. Somehow we'll do it, right? And I think like the kind of presentations we're seeing here, like this is my favorite. I can put up a really big tofu on the screen, and people are not just wait, they're nodding and saying, you can't do that. All right. So this is a follow-on presentation to Eric yesterday. I don't need to tell this group this. The importance and predictability at short time scales. And storage optimization, markets, getting things right in short term, which turns out to be really hard, is of increasing concern. I think it's only going to get more. Yesterday, Eric went really deep. Reviewed the slides. He gave a lot of detailed descriptions on how we build our solar cloud nowcast. Right. So how do you predict for 14 channels? Right. How do you predict the next frame of the satellite? Like watching a movie and it stops and then trying to predict what's going to happen next. Kind of what we did with the satellite. There's no NWP in there really. There is no other information. It's just satellite images and making predictions of satellite images. Right? And Eric showed that lo and behold, you can do a better job than in predicting the next frame of the satellite image, predicting the clouds with various famous. Not actually predicting the clouds per se, predicting the cloud maps, flying narrative and all the other channels, predicting the images as it is. You can do a much better job than option 12. Great. That's a paper. They would get published in BAM or anyplace else. But I run an energy forecasting. I'm like, that's great, Eric. Now we're going to take what came out of the grinder that made this, and we're going to shove it into our energy forecasting grinder, and then we'll feed it. All right, so that's what I want to talk about today. We picked up the great work that Eric did, and we said, does that add value to our forecast? All right, everyone in the world can show a graph. Right, you have a forecast system, it's got machine learning and AI, neural networks. So, here yesterday, you have flexible machine learning engine. Flexible machine learning engine, no, machine learning. Flexible machine learning engine. You've got your weather and your energy observation, like the situational awareness, right? What's going on right now? That's really important, but that doesn't tell you necessarily what's going to happen in the future. Right, then you got your NWP stack, on the left hand side. Okay, that's great at telling you what might happen in the future, but it's not perfect. Right? And it's got some real issues associated with short time, right? Her is like freaking incredible. Right, we were just having a sideboard conversation. We love her. We're so glad that we're going to keep it operational. Yeah, we're good. But by the time we get our latest term forecast from its initialization time, it's 2 hours old. Right? So we got to fill in the gap. For old people, it's like that Wendy's commercial. I mean, Wendy's favorite. Where's the beef? We need some sort of information about what's going to happen with the clouds into our flexible machine learning engine, because otherwise it's going to be like ChatGPT. Right? So ChatGPT the other day told us that if we want to have better cheese on our pizza, we should use filters. Okay. So now we have something, all right? We've got these satellite images, we've got forecasted satellite. We have this stack of information for model training, because all machine learning needs a ton of input data. We have a stack of these satellite images and forecast of those satellite images, all 4 parameters. We've got 5-minute intervals out to 3 hours. We make a new training-based forecast for that every 15 minutes. And then that's the training data set. When we go into real-time inference mode, we can just rapidly refresh this thing every 5 minutes. Right? Why is there a difference between training and refresh mode? Because there's so much autocorrelation to these images. You don't need to save or archive, every 5 minutes, every 15 minutes. So we've got this great new set of data that can shove into the new renewable energy forecasting AI. Okay, so now we're going to take a look at how we did, right? But let's first talk about some references and benchmarks, right? So in order of increasing skill, goal, we hope, right? You've got smart persistence all the way on the left-hand side of the screen. That doesn't have any CWT in it. It doesn't have any cloud casting in it. It doesn't have. Notice how cloudy it is right now. It's got that situational awareness. It knows the project metadata from the site, channel tracking, whatever. And then it knows some of the geometry. It does rise and set it. And kind of predict that. So that's smart persistence. It's a pretty good benchmark. It's a really good benchmark, actually, for things like that. Right. Then we've got our baseline. The thing that Vaisala runs today for our customers. So now we bring in long histories of GHI and energy data from the project. And we build machine learning models that just use that lag predictors, all that kind of stuff. We bring in the high resolution documentation. We bring in the ECMWF. We bring it in some of the top. We bring in the spread predictors. We bring in the UK Met Office. We throw everything you can get and call the kitchen sink in there and let the machine learning system figure it out. So there's a lot in there. That's our baseline. That's what we would sell a year ago to our customers. Today, we have the same sort of engine, but we have this cloud nowcast that Eric showed going in as an image. So a huge stack of satellite images in its forecast put into the image. So how good is our baseline? Before we talk about how good the cloud nowcasts are, how good is the baseline that we sold last year compared to more persistence? Well, fortunately, thanks to Emory, there was a trend, right? And we looked at that a little bit yesterday. So here's like CIA, FBI, highly redacted reports. I don't know if we need to be as careful about it. But number one conclusion, right in the top, basically looking at the day ahead, hour ahead, 4 hour ahead, and 2 hour ahead time horizon. The conclusion was we're all really good at that. Top forecasters, right? And we were in a good category. We know this is a good category. We figured out how to do day ahead forecast. Check, done. Right? Now, there are still issues. We were talking about them yesterday. There are where we all struggle, right? And this is in the report. Number two, some resolutions are more difficult to forecast accurately. Yeah, this really showed it. Right? So you look on the right-hand side here, this is hour ahead. So this is 1 hour ahead for a 5-minute interval. So you're basically doing a 60-minute lead for a 5-minute lead, 60 to 65. Right? And then the hour ahead 15 was 1 hour ahead, 60 minutes, 75 minutes. So you're kind of looking like this kind of time. This is where the participants will be judged, right? And that very bottom there, bottom row on the right-hand side shows you smart persistence of the preference. So 5-minute interval, hour ahead at 13.25% error, right? Most vendors were able to do about a 5% improvement over smart persistence. And that's not a lot of things. The winner was able to do a 13%. So that's the state of the art. Right? So how did we do compared to all of this? Well, I loved this chart. It was great. Please let's do more. we learned so much. One thing that we learned was that our sub-hourly forecast, the first 6 weeks of the trial, was gosh darn. Right, so we made some corrections, and then at the tail end of the trial, oops, sorry, too late, we did much better. So this shows kind of our performance. The lower scores here are better. Vaisala forecast performance is compared to the other 9 participants. And you can see, like, site number 1, we were right in the running, if not the best. Site number 2, we were off. Site number 3, right in the running, best. So our baseline performance was pretty good compared to the relative performance of the other vendors, right? Which is important. I'm about to show you some baseline forecast, right? And I don't want you to think, oh, well, you guys are bad at this. We're bad at everybody else, right? But this is the point. With doing these kinds of competitive trials, you really get some transparency. Everyone gets together, starts competing, right? And you have this huge opportunity to improve, right? For all of us to work together, it's all our challenges. We actually have to have more cooperation and more transparency to solve these challenges. We're all kind of sitting in our own silos and afraid to enter the marathon and make it our aspects. Well, we're not going to improve that. Okay, so some hourly resolutions more difficult to predict. All right, this is the statistics. This is the mean absolute error. Didn't I just hear yesterday that mean absolute error shouldn't be used to judge the quality of the forecast? I just stepped right into that. But here we go. That's what we do. That's what we look at. First thing, mean absolute error, right? So green line is the baseline. That was already competitive and skillful. The blue line is the mean absolute error of the cloud. Cloud now has the mean forecast. And it has about a 20% improvement over the baseline, right? And remember that the baseline could be smart percentage of 5 to 15%. Let's call that 10%, right? So we're looking at like a 30% improvement over smart percentage. We're kind of without the cloud now, you know, the average trial shows that vendors are able to get it out, you know, 10% improvement, you know, over smart percentage. In this business, usually people are all excited with 5% improvement. You get a 20% improvement, it's like, Eric, let me find you. Fantastic. Okay, but who was the author that said lies, damn lies? Exactly. I hate these graphs. You know, when with my forecasting team, I'm always like, let's look at some forecasts. And I have a great word for some forecasts. Like, let's not make stupid forecasts, right? And you can only tell whether you're making stupid forecasts looking at it. Like, does it actually look better, right? So I want to show you this. Okay, that should be easy to predict, right? This is the observed power generation on a perfectly clear day, right? So there's our baseline forecast. These are 3-hour-long forecasts, updated every 5 minutes. I just took a snapshot of some of them. And in the blue is the cloud cast. Okay, we didn't make stupid forecasts. Like first do no harm, right? We put all this new machine learning in, and we want to make sure that it doesn't go off the rails. Simple. You'd be surprised. You know, we were able to kind of dive into some of the numbers in this trial. You know, a large part of winning these forecasting competitions is playing it safe, right? To be able to actually get the shape of the clear sky data exactly right. If you have any kind of bias in this, it's going to score you in the mean absolute errors. So the winner is not necessarily the one that could predict clouds. The winner is the one that could predict clear sky days. But the utilities aren't really giving any value to predicting clear sky days because that is a very problem. They know that's coming. They want you to predict clouds. Right? So again, mean absolute errors is very useful. Okay, cloudy day. Right? So here's a cloudy day. A nice day outside there. That's our baseline forecast. Not bad. right? From an NAE perspective, the errors are like, who cares, right? The cloudcast enabled forecast did a better job, right? They had a better handle on the continued cloudiness in the middle of the day, as you would expect. But clear sky day and cloudy forward, right? What we get paid for is pretty clouds. Because in clouds are hard. It's not make any, make light of it, right? Clouds, predicting clouds on short time scales is really hard. We'll be working on this for a long time, right? So left hand side, this is like a stack of satellite images in our forecasts for southeastern United States. Right hand side, this is a partly cloudy day. This is where you get kind of all right. Eric actually showed this yesterday. That was our baseline forecast. Yeah, it was as bad as everything else, right? There wasn't there. Why was this so bad? Well, actually, it's not that bad. It starts often correctly, right? And then it tends to the high resolution, rapid refresh solution. That's all the information it really has, which has the day as being too cloudy, right? And that by the time you get that information from her, it's I have the information about where. So this is with all kinds of machine learning, they do tend to split the difference between. It's not that they're going to get all the variation up and down, right? But they're going to do a much better job, especially since we trained them in they're at understanding that actually it's not going to be cloudy. I don't see clouds right now, so let me hire the baseline solution, the difference down the middle, a lot we have to forecast. There are no flashes of this is just plain down. Right. So let me show another part. Blue again is the observation every 5 minutes. The red are the baseline forecasts. This is not very good. Better. Right? It does a much better job at that sort of big, depression there at the end of the day. It does a better job during the morning. It's actually got lines in it that it's doing the right things with the cloud that roughly the right time, right? It's by no means perfect. Sometimes my presentations are like yeah, sometimes it has flashes of brilliance. They're like, wow, look at that. It nailed it. It's great. The baseline forecast had no information whatsoever. Right. Now, we've really only just begun. We have the next version of this for our European domain. We continue to assemble more statistics. We're flipping out some of the machine learning core models so that they can make better use of much more complicated data sets. There's no stopping here. This is why this whole business is going to continue to be very fun. Okay, now that was just a couple of examples. This is what we saw. This is from our own internal for fun dashboards. Pay no attention to that big spike there on the left hand side. But this is skill score. This is our forecasts for a solar project relative to smart persistence as a skill score. So 0 skill means what are we paying? Negative skill is oh my god, horrible, right? And what you can see here is on March 22nd, we turned on Nowcasting. And the skill score for like a 60 to 75 minute horizon, that yellow line that you see, from about that 10% mean absolute error to about 10% skill score to about a 30 to 40%. And 30-minute ahead skill score, this was even part of the effort. 30-minute ahead went from 0, that's that orangish line that you see second bottom, went from 0 to actually being about 20% skill score improvement. There's a different site where we actually turn on the cloud nowcast even earlier. 60 to 75 minute horizon skill score went from that 0 to negative, that yellow line, to be basically being a skill score of 30 to 40%. 30 minutes ahead, we were, if you look at that orange line at the bottom, negative 20%. smart systems kicking. And with the cloud nowcasting, we were able to basically increase that to about 25%. So we went from purely dreadful to much, much better. And the 15 minute, this is incredibly hard to do. 15-minute ahead forecast for Renewable went from awful, you know, you can see negative 30% spill scores to about a spill score. So let's be in touch. If you're interested in trying it out, give us a call. And we'll be back next year to talk about this lesson learned. And there are conclusions here. I like to say these short-term forecasts are like children. Children, I have children, so I can be free to comment. Children are commission. You ever hear that thing? Everyone thinks their children are above average. Kind of a statistical joke, right? So there are children, so of course we think they're above average, right? They outperform the benchmark. There's occasional flashes of brilliance. They nail those ramps. Some of the child's art actually get put in the refrigerator. Hey, good job, you nailed that one. Wonderful. And just like children, there's lots of room for improvement, right? They are just starting to learn. Last thing I'm going to leave you with is, what if we could do the same thing for wind? Well, how do we do that with satellites? Well, what if we deploy a standing LiDAR? And what if we could see the wind coming? Or what if we shove that into the machine learning? I'll be back next year. Thank you.
Very interesting stuff. And now I'm going to turn things over to Chris Bremer from Storck Project in Arizona. He's going to talk about the impacts of soil forecasting on hybrid resource management. Chris.
Thank you. You guys hear me? Wonderful. As mentioned, my name is Christopher Bremer. I work at the Storck Project down in the Phoenix area. I'll give a quick introduction to Storck Project. Some of you might have seen the Joe's presentation earlier. A little bit of this, just for those of you not been here. We currently serve the eastern side of Phoenix area, split it with APS. I do want to call attention to where our major legal assets are into this, with the understanding of what the forecasts are actually predicting. We have quite a lot of resources all around the state. Most of our utility scale solar that we secure forecasts for are down there in orange boxes in the bottom right of the slide, heavily co-located and very, very close to our load, which is actually pretty interesting. If you do get clouds, you might see a little bit of benefit on the load side. You might see a bit of a dip in your solar generation. Currently, we have one pretty large wind resource in the northern part of the state, up there in to the northeast. We will have more wind coming in central Arizona here in the next year. Still in the commissioning phase of that, but we're quite ready yet. We are really focused on renewable forecasting right now, as we expect to triple the capacity of our renewables and storage resources going forward. So our thermal fleet is going to remain largely the same. And so this is driving really focus on forecasting. It will be very, very critical to the dispatch and scheduling of our resources. And finally, really want to draw attention to the comment of this presentation, which is the evolution of dispatchable based resources. So rather than just adding on solar standalone, wind standalone, we do recognize that there's a strong need for a lot of energy storage, for batteries, maybe solid state batteries, hydro, things of that nature can help us to manage how much renewables we have, and can actually give us some benefits and change the way that we view our forecast accuracy and how we use forecast in an operation and scheduling perspective. So a really big growth in terms of the dispatchability of these solar and storage resources. By far the biggest flavor that we have right now, as of the last year, are hybrid resources. This is a very particular flavor of solar plus storage resource within the context of us, the Western Energy Balance Market and Vaisala. So this is where you have a solar and a battery resource that are one big giant resource to us, the utility. There's a plant controller that takes a singular set point from our EMS system, and it's the responsibility of that plant controller to divvy that up between the solar and storage components, and we need to comprehend that logic in our scheduling so that we get out the point of interconnection that we expect. And what this does is it changes the way that we need to view the forecasts for these hybrid resources. And that's the topic of this. So you see, starting with the solar forecast, there on the left, that's sort of starts the entire hybrid scheduling process. You start with your solar forecast, maybe this is the day. Our scheduling engine takes a look at that, it takes a look at the load forecast for that day, and it generates a battery schedule that it keeps to itself. It then adds those two things together to generate a net interconnection schedule. And that's the base schedule for the hybrid resource. You might notice that the battery here is going to provide a little bit of regulation for that solar. And so one of the interesting things about hybrids that we've noticed is that we actually don't need to chase a perfectly accurate solar forecast for these hybrid resources. We do need to make sure with a few caveats that they don't stray too far. But as you can see here on this slide, the forecasts are now gray and the actual are orange. As long as those errors are bounded and relatively unbiased, the battery can swing a little bit, charge a little more, discharge a little bit as needed, such that the point of interconnection energy out is always met. And so this really changes the way that we forecast for these resources. And to take it out of the Excel fonts, this is what that looks like for an actual day. This is a spring day at our Sonoran hybrid resource. West Valley, you can see it was a very intermittently cloudy day. We had a lot of in the orange there and an orange line, but you have a lot of variability throughout the day. Cloud induced ramping, a lot of cumulus clouds hitting your solar. We were able to grid chart the unit in the morning, so we did serve morning peak in the spring. And the battery, over the course of the day, swung its charging set point up and down to counteract solar. So we did manage to reduce our solar ramping in the grid cycle by an order of magnitude. So you see that the blue line is your net to grid, at least to our schedule, like blue. And our solar forecasts on this day were not perfect. We did see a pretty error here, but we still managed to stick to our schedule. We had a nice evening discharge of a full battery condenser. So here was a day where intermittently cloudy, had forecast error inherent in it, but it didn't really matter for this particular resource type, which is that solar plus storage hybrid resource. Now, one of the things that we are worried about is instead of chasing a sort of perfect forecast, we do want to make sure that we capture sort of the gist of what's going to happen, or we can experience a few issues. So this is where we start to worry more about forecast bias during certain times of the day than just about error, right? So here in this particular day, you notice that we did have some mid-afternoon clouds. They were pretty thick. And so solar actually dipped quite a bit below what was scheduled for the day. This actually caused the battery to discharge slightly, and that's in that red shaded area where battery power crosses zero, positive, begin to discharge to the grid. The schedules didn't have enough time to compensate for this. It's already kind of the end of the day. And so you couldn't really suck up more solar power. See, it made a try to there, 18, dip a little bit. But this manifests as an energy shortfall at the end of battery discharge. And so you see that we took what was solar forecast error at like 3 p.m., 4 p.m., and we turned that into an energy shortfall later on in the evening, which, by the way, you had many hours of notice ahead of time, right? You can see that your SOC at sundown is only 80%, 90%, and you can see that coming. I just included the set points here from the day, just for illustrative purposes, in that green shaded area where that shortfall occurs. So you can kind of transform the problem statement. Biased low forecasts bring their own complexity here. So the battery resources here, they have a max charge rate, and it's dependent on the relative size of your solar and storage resources compared to each other and the point of their connection. If we ever get one particular hourly interval wrong enough, that the base schedule is so low that the battery can't hit it, it is going to be forced to curtail solar. So in this, for these hybrid resources, it will do everything it can to give you your set point for that particular hour. And here on the left, you see that it did need to curtail solar. We had such a low schedule and a clear sky day that it was forced to curtail. That same theme on an hourly clear sky day is extensible to intra-interval variability there on the right. So even if your forecasts deterministically median are perfect for a particular interval, if you don't capture the highs, all of the highest peak within the hour, you will curtail those as well. Because again, the battery can only charge so much, and you need to comprehend that intra-interval variability in your base scheduling process. We also have a few midterm constraints, and this brings some additional complexity for some longer term forecasts, where you might have a max number of annual cycles, but you might have a sort of maximum average annual state of charge. That might dictate, do you want to charge more in the morning? Can you do a full cycle on this day, or do you need to restrict some of the battery SOC from being used? And we do then consume a lot of these, several months out, maybe historical data from other solar sites that have good representative data, some sort of TMY, typical meteorological use, and we run a midterm model we use to also inform our daily scheduling process. That'll help us understand, can I go for a full charge? Do I need to empty the battery right away? Can I do it some overnight, following morning? So there's this one more layer of sort of midterm constraints that we develop using a midterm production cost model for these hybrid resources. To sum up, because it's quite a lot here, hybrids have a really different set of objective functions for our renewable forecasts for the solar components. Unbiased solar forecast error is not all that much of a problem, as long as it's bounded. Typically less than like 15% of batteries' power capacity are fairly tolerable within a day. We don't need to go chasing that past 1% forecast error 2 hours ahead. We can kind of tolerate that here, but we care significantly about biases. So if your forecasts are high, you might shortfall later, schedule aggressive enough to charge up the battery. If they're low, you may take an immediate economic penalty in terms of solar curtailment, because in order to hit that set point, you may be forced to curtail solar. And we also need to comprehend intra-interval variability within the scheduling process. So even with perfect forecasts, if we have an intermittently cloudy day, you can still curtail solar, even if your hourly forecasts are absolutely spot on, depending on the size of the battery and where it's scheduled in its charging regime for that particular battery. What we're doing about this is we have a strategy to use biased high forecasts to avoid solar curtailment. So as I mentioned earlier, we do sort of see that energy shortfall coming towards the end of evening discharge. And so it is typically more permissible for us at SRP right now, given current conditions, to go ahead and avoid curtailment. It's okay if the battery's a little bit undercharged. We want to take as much solar as we possibly can and not pay, especially with the PTC penalties that add even higher costs to curtailment. We want to use a biased forecast for our vendors to prevent that curtailment. And then we also do consume an intra-interval variability forecast from our vendor as well. And just like you saw from the Meteor Systems presentation just a few minutes ago, this is an ensemble forecast here. There's lots of different initialization runs of the GFS and the PER, giving us different spaghetti plots and what's that. We want to comprehend the upper and lower bounds of that. To make sure that these new forecast products are accurate in the sense that they are biased, right? So now you're using a biased type of forecast. And they supposed to be. Dispatch, as you might have noticed, all of those screens that I showed were hourly based schedules. That's currently what we are using for our hybrid resources. It actually works pretty well because the batteries can provide kind of their own reserves. And you see that there on the left, this sort of, T-minus 75 minute based scheduling that I'm sure many of you are familiar with, if you're part of Western EIM or familiar with the TISO scheduling process, real-time scheduling. There are structures and market structures for sub-hourly dispatch and finer tuning of our batteries. And this would help enable us to get like a little bit more charge if we wanted to at closer time horizons. So rather than being so far out at the hours ahead, we could use a 5-minute forecast as they just mentioned. You get much more accurate forecasts on that really close time horizon for sub-hourly. Hours ahead, sub-hourly doesn't really work all that well. But if we can go at a 20-minute time horizon with a 5-minute forecast, get a little bit more charging. We think that we can have the best of both worlds, right? Deal with your solar forecast error and also get your battery to full charge right at sunset when you need it, so that you have it over the evening. And then finally, a little plug for anyone else who might be interested. We do have quite a bit of ongoing research, partnering with EPRI, partnering with local research institutions to try and do some forecast improvement on our own. Not just also working with our vendors, looking at some convolutional long short-term memory neural net for sky camera. So rather than satellites looking down, we have sky cameras looking up to help us with our nowcasting capabilities for that 5-minute dispatch. We're also looking at aerosol and dust impacts, a little bit unique to the desert Southwest maybe. We get these big rolling dust storms that have huge implications on solar power. It's not really a cloud. It's kind of this big dust wave that will come sweep over the valley with our monsoons. So a little bit of a unique forecasting need there. And then we also are working with EPRI on dynamic reserves, as well as risk assessment of our forecasting error and intra-interval variability at a system level. So if anyone's interested, we're always happy to partner with your utilities, anyone out doing research on any of these topics. So there's a lot to come for SRP for forecasting moving forward. And thank you. That's the end of my talk.
Great.